Okay, so when we last left off, we discussed various methods to prepare esters, and one of which was going through the corresponding acyl chloride or acyl halide. In this lecture, we're going to be discussing methods to directly prepare esters from the corresponding carboxylic acid via reactions such as the Fischer esterification. So the Fischer esterification is quite an interesting reaction in that it's a carbonyl substitution reaction that occurs under acidic conditions. Reaction of an alcohol and a carboxylic acid gives an ester and water. Importantly, as noted for this reaction, it's an equilibrium process and thus an overall reversible reaction. Generally, due to the strongly acidic conditions required for the Fischer esterification, you're limited in your alcohols to primary alcohols, be it methyl, ethyl, propyl, and butyl alcohol to make the corresponding methyl, ethyl, propyl, and butyl ester. So generally, you're limited to primary alcohols. Because if you had a secondary or tertiary alcohol under the strongly acidic conditions, you would protonate the alcohol, and then you'd likely see elimination via an E1 pathway. Does that make sense to everyone? Why, because we're working under strongly acidic conditions, why we're limited to primary alcohols? Does this idea make sense? Perfect. So let's keep going with this idea. And let's talk a little bit about the mechanism behind the Fischer esterification. So it's a textbook carbonyl substitution reaction run under acidic conditions. So for our first step, we're going to protonate the carbonyl oxygen. This activates the carbonyl and makes the carbonyl carbon substantially more electrophilic than usual. From here, because we've activated our carbonyl via protonation, even weak nucleophiles, such as this alcohol, can readily attack the carbonyl carbon and generate this tetrahedral intermediate. Now, as our end goal for this process is to substitute our added alcohol for the hydroxyl group, we're going to engage in a series of proton transfers. First, to free up a lone pair on our oxygen atom, and then subsequently to activate this hydroxyl group as a leaving group. Protonation generally activates groups as leaving groups, and in turn, because we've protonated this hydroxyl group and we now have this water motif, we can readily kick out water, which is a great leaving group, and generate our protonated ester. After deprotonation of our carbonyl oxygen, we can isolate our desired product ester. Does this mechanism for the Fischer esterification make sense? It's the typical pattern for an acid-catalyzed carbonyl substitution reaction. Note, this entire reaction sequence is an equilibrium process. And what we'll talk about next are methods to drive the equilibrium towards the desired ester product. So, any initial questions? Any questions so far? If we don't have other questions, let's keep going then. And let's talk a little bit about applying what we've learned to solve a problem. So in this case, we're given the following reaction. In this case, we have a carboxylic acid and an alcohol, and we're heating this mixture under acidic conditions. So These are textbook conditions for a Fischer esterification. So I'd like us to, considering this carboxylic acid and alcohol substrate, I'd like us to predict the product from this reaction and then try to draw a reasonable mechanism for this reaction. So let's take about 3 to 4 minutes to work through this example, and then I'd like students to share their proposed responses or any questions that they have in the chat, verbally, or annotated directly onto the class whiteboard. So let's work through this example, and then I'd like to see some student questions and student responses shared in the chat, verbally, or on the class whiteboard. So we have butanoic acid and ethanol, and we're combining them under acidic conditions, and we're heating this mixture. So we're dealing with a textbook Fischer esterification. So what product would we observe, and would anyone like to volunteer and annotate a mechanism for this reaction? You can also share a photo of your written work for this problem in the chat. So as we're under acidic conditions, the student's noticing that if we have a carboxylic acid and we want to substitute the carboxylic acid alcohol for our alcohol component in solution, we're first going to activate our carboxylic acid for reaction via protonation of the carbonyl oxygen. Now our carbonyl carbon is substantially more electrophilic, and as a result, it can be attacked and it can react with even relatively weak nucleophiles. So in this case, we have our nucleophilic alcohol, ethanol, and ethanol can easily attack the electrophilic carbonyl carbon. Yeah, I would draw the lone pair on ethanol, but yes, I get what you're trying to convey. Okay, from here we have this tetrahedral intermediate. And the student's still drawing out their mechanism. I'm just trying to narrate as the student draws out their mechanism, just to help everyone stay on the same page. So we have this tetrahedral intermediate, and let's see what's going to happen next. What does the class think? So we have this tetrahedral intermediate. We want to eventually kick out water. So how do we accomplish that? How do we set up our substrate? So the student's drawing that we're pulling off a proton. I believe in the product that they've drawn, they're missing a proton. Yeah, there we go. Perfect. So we have a relatively acidic proton on our ethanol oxygen. So our base can pull off the proton. In this case, there's something a little bit more basic in solution. In this case, I would probably draw it with ethanol pulling off the proton, because that's slightly more plausible as a base under these conditions, because ethanol is substantially more basic than chloride. But otherwise, the basic idea there is perfectly reasonable. We're going to pull off a proton, and now from there, we just have to figure out how to activate one of our hydroxyl groups as a leaving group. So I'm just narrating as the student draws out this mechanism. So in this step, our ethanol is going to pull off a proton. Yep. We've now just need to activate our hydroxyl group as a leaving group. And as we're under acidic conditions, what's the most logical way that we can activate this alcohol? Yep, exactly right, via protonation. Wonderful. So in this case, we'll protonate one of our hydroxyl groups. Again, I would draw the lone pair just because that's the actual set of electrons being used to form that new bond. Yep, so we protonate our alcohol. Wonderful. We now have a pretty good leaving group. So what can happen next? Now that we have this wonderfully activated leaving group, what can we do with that leaving group? Remember, for carbonyl substitution reactions, carbonyls are generally quite stable. So we prefer, if possible, to reform the carbonyl. So as the student's drawing, we're going to kick down a lone pair and lose our leaving group. In this case, water is a better leaving group, so we lose water. Wonderful. From here, we have our protonated ester, which just requires one more cleanup step to get our final product. So we typically don't isolate positively charged species. So as a cleanup step to get a neutral isolable product, all we have to do is deprotonate our ester, and the student's drawing out, in this case, ethanol as a base, perfectly reasonable. Has a reasonably basic lone pair, so we can pull off our proton and get our desired neutral isolable ester. And I appreciate the fact the student drew equilibrium arrows throughout this mechanism. Though if you use an excess of alcohol, you're going to get the ester product almost exclusively. And we'll talk about that in a moment. So this student proposed mechanism looks great. So allow me to clear these annotations and just redraw this mechanism for our reference. So in this case, we have our carboxylic acid. So as we're dealing with a carbonyl substitution reaction under acidic conditions, our first step is to protonate our ester carbonyl. From here, we've now activated our carbonyl carbon for attack with common nucleophiles. In this case, our solvent ethanol is more than sufficient to serve as a nucleophile and attack the electrophilic carbonyl carbon. Now, we have to engage in a series of proton transfer steps, both to free up a lone pair on our oxygen atom and to activate our hydroxyl group as a leaving group. You can show the proton transfers in a single step or two discrete steps. Either is okay stylistically. Okay, so we pulled off a proton from ethanol. Now we're going to protonate one of our hydroxyl groups, and that in turn activates our hydroxyl group as a leaving group. Water is a pretty good leaving group, so it can be readily kicked out and lost. So we'll kick down our lone pair, lose our leaving group, and reform our carbonyl. From here, we're just one quick cleanup step away from getting our desired ester product. So with that, we've drawn out the full mechanism for the Fischer esterification, and we've correctly predicted our product. In this case, it would be ethyl butanoate. Does this mechanism and does this example make sense to everyone? Any questions on this example? Any other questions or comments that I can address before we move on? It's great to see students participating and proposing mechanisms, as the student proposed mechanism was perfect for this example. Okay, let's keep going and let's talk a little bit about this idea of equilibrium. This is going to be review from general chemistry too, but it's important to talk about how principles of equilibrium in Le Chatelier's principle are applied for organic reactions. So, because this reaction is an equilibrium process, we know that there's a steady state concentration of reactants and products at equilibrium. Now, the equilibrium constant provides us the ratio of each concentration of each species participating in the reaction in solution at equilibrium, accounting for stoichiometry, of course. Q is the reaction quotient, which represents the current observable concentrations of each species in the reaction mixture. And based on the relationship between your reaction quotient and your equilibrium constant, we can predict whether the equilibrium will shift towards the reactants or products. Okay. So let's talk about this in more practical terms and introduce the idea of Le Chatelier's principle. Generally, this idea is that if equilibrium is disrupted by changing the concentrations of reactants or products, the system will react to reestablish equilibrium. So for example, Q is our reaction quotient, which is the current observable concentration of each species in solution, and K is the equilibrium constant, which are the concentrations of each species in the reaction at equilibrium. There are three main cases that we'll talk about in the context of the Fischer esterification. If Q is equal to K, the system is at equilibrium. If Q is less than K, the reverse reaction occurs and reactants are favored. So Q is greater than K, the reverse reaction occurs, and if Q is less than K, the forward reaction occurs and products are favored. Okay. So now that we've defined these basic definitions, how can we influence this reaction to favor the products? Well, let's take a look. So when we compare the reaction quotient and our equilibrium constant, we want Q to be less than K for a product favored reaction. Okay, so in general, we want the concentrations on top of this equilibrium constant expression or reaction quotient expression to be small, while the concentrations on the bottom of this reaction quotient expression, we want to be, rather than small, we want them to be large, right? The smaller your numerator and the larger your denominator, the smaller the value of Q. So then, how do we accomplish this practically? The first way is by using a large excess of alcohol. The alcohol can be used as the solvent, co-solvent, or in large excess, right? If this alcohol concentration is large, Q will be, in turn, very small. You can also affect the concentration of water by removing water from the reaction as it's produced. This can be done via azeotropic distillation or by using drying agents. Right? If the concentration of water is small, Q will be small, Q will be less than K, equilibrium will shift towards the products. The final method, although it's far less common, is to remove the ester from the reaction as it's produced via distillation. This is used less often, though we would note that esters typically have lower boiling points than carboxylic acids, so the esters can be distilled off as the reaction proceeds. The only problem with this method is generally you'll end up co-distilling over some of your alcohol, so it's trickier to do in practice. Okay, so with that said, Generally, for a Fischer esterification, they're run with an excess of alcohol, and they're run either in the presence of an external drying agent or under azeotropic distillation conditions. We need to get rid of the water, and we need to have as large of an alcohol concentration as possible in our reaction mixture to help drive this equilibrium towards the products and help favor our desired ester product. Does this idea make sense to everyone? The Fischer esterification is an equilibrium, and we can drive that equilibrium towards the product by using an excess of alcohol and by removing water. Does that idea make sense? Any questions on this discussion of Fischer esterification and equilibrium constant? Okay, perfect, perfect. I'm glad it looks familiar from 102. Okay, so practically, let's talk about how we apply what we've learned and how we apply Le Chatelier's principle to get productive Fischer esterification reactions. The first case is by using a large excess of alcohol. So you can use 100 equivalents of methanol in this Fischer esterification, and that drives the equilibrium towards the product. Another case, which is a little bit more interesting, is when you have and you're trying to form a lactone. So intramolecular esterification reactions are product favored. That's because even though your alcohol is attached to the same molecule, and you may say, well, the concentration of the alcohol doesn't appear to be that large if you measure the concentration just in terms of mole per liter. But for intramolecular reactions, because your carboxylic acid and your alcohol are tethered close together, you have effectively a high effective concentration of alcohol. For intramolecular reactions and intramolecular Fischer esterifications, because your alcohol and carboxylic acid are tethered, they're more likely to collide, they're more likely to interact with each other, and thus you're more likely to see a reaction. It's as if you had a very large excess of alcohol in terms of effective concentration, because your alcohol and your carboxylic acid are held close together. Does that idea make sense? Generally, if we think about rate of reactions, intramolecular reactions are way, way faster than intermolecular. Does this principle look familiar to everyone? Does this principle seem familiar? Any questions on these two applications of Le Chatelier's principle? Perfect, perfect. So, for those who are curious, well, how do we practically remove water under these cases? The most common method is to run these Fischer esterifications under what are known as Dean-Stark conditions. To answer the question, yes, intramolecular reactions are reactions between two functional groups in the same molecule. Now, back to Dean-Stark conditions. So in this case, one way to drive this equilibrium towards completion is to remove water. And in this case, we can remove water from the reaction as it's produced via azeotropic distillation using what's known as a Dean-Stark trap. So toluene is really important in this case because we can generate a toluene and water azeotrope. As we discussed all the way back in Chem 112, toluene and water distill over as an azeotropic mixture with a unique boiling point based on the azeotrope's composition. As the reaction mixture is heated, it will begin to reflux. And over time, we'll begin to capture some of the distilled toluene and water in a Dean-Stark trap, shown here in this picture. One thing to note is that water has a density of 1 gram per milliliter, while most organic solvents have a density of less than 1 gram per milliliter. So your solvent, such as toluene, will be less dense and will sit on the top of the Dean-Stark trap. The water, which is more dense, will float to the bottom of the Dean-Stark trap. And so we can remove the water without completely emptying all the solvent from our reaction. So essentially, a Dean-Stark trap is just a very fancy way to remove water as the reaction proceeds. And it's a wonderful method to drive equilibrium processes to completion by removing water. You'll see this again in the context of aldol reactions and dehydration reactions. So, does this idea that we can remove water and drive the equilibrium for the Fischer esterification reaction towards the product ester, does that idea make sense? Does that concept make sense to everyone? Any questions on this idea? Okay, so let's keep going then. And let's talk about the reverse reaction. So acid catalyzed ester hydrolysis. So hydrolysis refers to the cleavage of any bond via the addition of water. If the catalyst is an acid, the product of ester hydrolysis are a carboxylic acid and an alcohol. Ester hydrolysis is the reverse of Fischer esterification. And we'll note hydrolysis is favored when 2 conditions are met. So let's just rewrite our equilibrium constant expression. So the equilibrium constant is water, our ester, our alcohol, and our carboxylic acid, right? So we have our alcohol plus our carboxylic acid in equilibrium with the ester and water. So with this in mind, if we want a reverse reaction, if we want to favor our carboxylic acid, so in this case, we want Q to be greater than K. So if we want Q to be greater than K, what 2 things need to happen? So if we want Q to be greater than K, in this case, we need to have a large concentration of water. What's another way for Q to be greater than K? What does the class think? What's another way for us to drive this reaction to favor our carboxylic acid? The Fischer esterification and ester hydrolysis are 2 sides of the equilibrium. We talked about for Fischer esterification and for the ester to be favored, we need to have a large excess of alcohol. If we want the carboxylic acid and hydrolysis to be favored, we need a large amount of water. Basic conditions are actually an entirely different process. And we'll talk about that in a moment, but yes, that is a potential method to promote the hydrolysis. What's another way looking at this equilibrium? A large amount of carboxylic acid would actually push the equilibrium towards the products. A small amount of alcohol, yeah. A small concentration of alcohol, sure. Yep. You can also use a large concentration of our ester. Practically, if we had to look at these three options, what's the easiest option to go with? What's the easiest fix? Water, by far. You just dump in an excess of water, you add your acid, and you heat the mixture. And because if we use an excess of water, Q is greater than K now, the equilibrium shifts to the reactants, and we see hydrolysis rather than esterification. There's actually a pretty fun lab that you can do where you run a Fischer esterification, you take an IR, then you add some water, you heat it for a little bit, and you can see the IR shift go back and forth from the carboxylic acid and the ester. It's a really fun lab. We'll see an example of that in the nylon synthesis. Yeah, if you have the right setup, you can view it in real time. Anyway, so ester hydrolysis is the reverse of Fischer esterification. So we treat an ester and water under acidic conditions, and that gives us our carboxylic acid and alcohol. So this is the exact reverse of the Fischer esterification. And as we'll see when we draw the mechanism, it'll look like the reverse of the Fischer esterification. So here is the mechanism. First, as with any acid catalyzed carbonyl substitution, we are going to protonate our ester. By protonating this carbonyl oxygen, we activate it for reaction with even weak nucleophiles. Now, water can come in and attack the electrophilic carbonyl carbon. And now, in this case, we're aiming to produce our carboxylic acid. So we have to activate this ether as a leaving group and free up a lone pair on our alcohol oxygen. So we're going to pull off a proton, and then we're going to protonate the ester oxygen atom. That in turn activates this alcohol as a leaving group. And then from here, we can kick down our lone pair and kick out our wonderful protonated leaving group to regenerate our carbonyl and generate a protonated carboxylic acid. This is a highly acidic species. So in the last step, water will pull off a proton, and that gives us our desired isolable carboxylic acid. Does everyone notice how this overall mechanism for ester hydrolysis is the exact reverse of the Fischer esterification? Does that make sense to everyone? Does this mechanism make sense? Are there any questions I can address on this mechanism? So if we don't have any other questions, let's try to apply what we've learned, in this case, to the following example. So in this case, we have this pretty complex ester, and we're treating it with hydrochloric acid, water, and heat. So I'd like us to predict the products from the following reaction, and I'd like us to draw a mechanism for this reaction. So let's take about 3 to 4 minutes to work through this example, And then I'd like students to share their proposed responses in the chat, verbally, or annotated on the class whiteboard. And of course, if you have any questions, don't be shy to ask them in the chat or verbally. So we have this complex ester, and we're treating it with hydrochloric acid and water. What products would we observe, and what is the mechanism for this reaction? So let's take a few minutes to work through this example. And then of course, I'd like students to share their responses in the chat, verbally, or on the class whiteboard. And if there are any questions that you have as you work through these examples, don't be shy to send them my way. So we have a student beginning to annotate their proposed mechanism. So in the student proposed mechanism, first, they're going to protonate the corresponding ester carbonyl oxygen. From here, that reactive carbonyl carbon can be attacked with nucleophiles such as water. And to help explain why, in this case, hydrolysis is favored, it's simply because we have such a large excess of water that will generate this tetrahedral intermediate many times. And each time we could choose to kick out water or the alcohol. And because we have such a large excess, of water, then in essence, statistically, we're more likely to, when we do kick out this ester complex alcohol, we're very unlikely to reform the ester. One thing I noticed in the student mechanism, when they drew the arrow, I would always make sure to draw the arrow from the oxygen lone pair because we're forming a carbon-oxygen bond in this addition step. Would the student be able to redraw their molecule to reflect that? Yes, but let's redraw the product to reflect that, right? Because since we're forming a carbon-oxygen bond, yep, perfect. You can use H3O plus or HCl. Both are viable. Though if you have an excess of water in acid, then you're more likely to have H3O plus rather than pure HCl in solution.
Professor, I have a question.
Yes, please go ahead.
So are we assuming that the H3O plus is coming from the HCl and the H2O combined, or?
Yes, that's correct.
Okay, thank you.
Generally, if you have a strong acid in water, you'll generate a large amount of H3O plus. So looking at the student proposed mechanism, they showed the addition of water and are now showing a series of proton transfer steps. First, to free up a lone pair on oxygen and to activate the ester alcohol as a leaving group via protonation. From here, now that they've set up this substrate, we're now ready for our key step, where we collapse this tetrahedral intermediate and we kick out in this case, an alcohol. So from here, after we kick out our protonated alcohol, we're left with our protonated carboxylic acid. And from here, we're just one cleanup step away from getting our final desired product. Perfect. So this student proposed mechanism looks completely reasonable. So let me just clear those annotations and let's redraw this mechanism. So stylistically, when you have a large excess of acid in water, or even catalytic amounts of acid in water, you're going to generate a fair amount of H3O+. And that's known as the leveling effect, where in effect, because you have a solvent that can accept a proton and generate a less acidic species, the strongest acid that can exist in solution is the conjugate acid of your solvent in most cases. Okay, so following this mechanism, we're first going to protonate the ester carbonyl oxygen with our acid. From here, we've now activated our carbonyl carbon for addition and attack with a range of nucleophiles. So water will attack and will generate this tetrahedral intermediate. From here, we're going to engage in a series of proton transfer steps. The first of which is water will pull off a proton. Note, you're highly unlikely to kick out something like hydroxide when you're working under acidic conditions. It's always important to be considerate when you're drawing your mechanisms and to just think carefully about, are the reaction conditions compatible with the intermediates and species that you're drawing? Okay, so our end goal is to kick out this alcohol. So we're going to protonate that alcohol. Protonation generally activates species as a leaving group. Okay, from here, our tetrahedral intermediate can collapse and we will kick out our alcohol. And then as a cleanup step, we're just going to pull off our proton, and that gives us our neutral isolable carboxylic acid. The reason why we see hydrolysis in this case again is because we have an excess of water. Does this make sense to everyone? Any questions on this mechanism before we move on?
Is there a reason why the tetrahedral intermediate collapses like first before oxygen gets deprotonated?
Yes, because we're under acidic conditions, we're highly unlikely to have alkoxide ions floating around because those are basic species, right?
Oh, okay. That makes
So
sense.
if we have strong acid, the alkoxide ion would likely get protonated almost immediately.
Okay.
Mhm.
Thank you.
Perfect. Any other questions that I can address? Okay, so let's keep going then. And let's talk about the conversion of carboxylic acids to amides. And there's an easy way and a hard way. The first and most obvious idea is direct reaction of a carboxylic acid with an amine. The problem stems from the fact that you'll likely just see acid-base reaction rather than carbonyl substitution. Thus, generally, you'll isolate the carboxylate salt rather than the amide. At high temperatures, for substrates that tolerate high temperatures, the amide can be formed with the loss of water. This is known as pyrolysis. I would not recommend this as the go-to method to prepare amides because many substrates are quite sensitive to high temperatures. So does this discussion on the direct synthesis of amides make sense? So generally you see acid-base reaction rather than carbonyl substitution. At higher temperatures, you can form the amide with loss of water via a reaction known generally as pyrolysis. This is not the way most people prepare amides. This is not the go-to method. It's pretty low on the list. But does everyone get this first discussion of the direct synthesis of amides? Any questions on this discussion? Well, there's no mechanism drawn. I wouldn't use this as a go-to synthetic route because in many cases, high temperatures may promote side reactions on your substrates that can cause decomposition. What we're going to talk about next is the go-to method to prepare amides. And one of the most common is via activation of your carboxylic acid. Now, there are many reagents that can accomplish this. The most common class are these diimide reagents, such as dicyclohexyl carbodiimide, otherwise known as DCC. And what DCC does is it activates the acid and converts our carboxylic acid alcohol into a great leaving group. Now, in terms of mechanistically how this happens, we'll talk through the mechanism for a DCC catalyzed amide formation at this moment. So DCC, which is a diamide, has a basic nitrogen, which can pull off a proton from our carboxylic acid. From here, our carboxylate can then attack the electrophilic imine carbon. Remember this motif where you have a carbon nitrogen double bond is known as an imine. When protonated, it's an iminium. And these iminium species are highly electrophilic at carbon. So they can be attacked with nucleophiles, such as our carboxylic acid oxygen. From here now, this carbonyl carbon is reasonably electrophilic, and it can be attacked with nucleophiles, such as an amine. From here, when our tetrahedral intermediate collapses, we have the choice between kicking out this ammonium leaving group or kicking out this essentially urea-like leaving group. Now, if we think about our two options, one of the reasons why we kick out this activated leaving group stems from the fact that when we look at this urea leaving group, what do we notice about this leaving group? Is it stabilized or destabilized? Does this look like a good or bad leaving group if we look at this DCC urea derived leaving group? Does this leaving group look relatively stable? It's quite stable. This negative charge is delocalized over multiple atoms. This doesn't look like a particularly strong nucleophile, doesn't look particularly basic either. So it's a pretty good leaving group. And this is really important because the reason why DCC is quite effective for these amide coupling reactions is because it converts a poor leaving group, such as hydroxide, into a great leaving group, such as this urea-like motif. From here, after we kick out this DCC-derived leaving group, we get this dicyclohexyl urea product and our desired amide. Just to show that last step, this protonated amide is quite acidic, and as such, it can be readily deprotonated by our dicyclohexyl urea byproduct. That gives us our desired amide cleanly. When if we tried this reaction on the normal carboxylic acid, we'd see competing proton transfer reactions instead. So DCC does two key things. First, it serves as a base. Then it activates your alcohol as a leaving group. And most importantly, the byproduct generated is not sufficiently nucleophilic to engage in reverse reactions. Does this make sense to everyone? Does this mechanism for DCC catalyzed amide formation make sense? I like to think of DCC in the same vein as thionyl chloride, in that it converts an alcohol into an effective leaving group, and it gets rid of the problematic acidic proton found in the carboxylic acid motif. Any questions on this mechanism? Okay, so let's keep going then. And let's try to apply what we've learned here to predict the products from a reaction and to draw a mechanism for this reaction. I'm just going to redraw the structure of DCC, which is something that you're going to want to be familiar with. This is a super common method for preparing amides and for amide couplings in the context of amino acid and other biologically relevant amides and carboxylic acid motifs. So here's the structure of DCC once again. So we have a carboxylic acid, in this case butanoic acid, and an amine, in this case ethylamine. And we're treating this mixture with DCC and pyridine. Typically you add the DCC before the amine, but that's just a side note. Let's try to predict the product from this reaction and draw a mechanism for this reaction. And interestingly enough, this mechanism and this general mechanism can also apply for using DCC as part of esterification reactions. Because once you've activated your carboxylic acid, you can do whatever you want with that activated carboxylic acid. So you can use a range of different nucleophiles. It's most commonly used with amines, however. Okay, so let's work through this example, and then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And if you have any questions as we work through this example, don't be shy to ask them in the chat or verbally. As one other note, DCC and other related reagents can also be used to activate just normal alcohols for substitution reactions. So it's really quite a versatile reagent. Though we don't do any DCC couplings in the lab because it has to be handled pretty carefully to avoid an allergic reaction. So, does anyone have a proposed mechanism that they'd like to share? Or does anyone have a question that I can answer to help advance our discussion? No worries, no worries. I just like to see students start attempting these problems so I can get a sense of what questions that they have, or if there are any parts that I can provide feedback on to help advance our discussion. So in the first step, the student showed DCC deprotonating our carboxylic acid. This carboxylate salt is now substantially more nucleophilic than the parent carboxylic acid. And we've also activated DCC. Rather than having an imine, we have an iminium ion. So from here, now that we have this activated iminium species, our iminium ion carbon can be attacked with nucleophiles. One thing I would note, the mechanism, the arrows look good, but since you showed protonation of DCC in the previous step, please show that proton attached to one of your iminium ion nitrogens. There we go, perfect. And that helps explain how DCC has been activated for reaction with even a weak nucleophile such as carboxylate. From here, we now have the DCC adduct. So let's draw the structure for our product, and then let's continue on with this mechanism because this student mechanism is looking great so far. I'd like the chat and the rest of the class to help chime in and help provide suggestions as this student is working through the mechanism. What happens next? Now that we have activated our alcohol by forming this DCC adduct, we now essentially have urea as our leaving group, and that's a pretty good leaving group. What's going to happen next? From here, ethylamine will attack the electrophilic carbonyl carbon. We have students in the chat saying that a lot. I see a lot of lines asking for addition of ethylamine. From here, we have this tetrahedral intermediate. And because we're under basic conditions, it's reasonable to draw this alkoxide species. Now we have a choice. We have two leaving groups. We can either kick out ammonium or this urea-derived leaving group. So what leaving group do we kick out? What's the better leaving group? Yep, we kick out the DCC-derived urea leaving group. And so when this tetrahedral intermediate collapses, we generate dicyclohexyl urea and the desired amide. However, we still have one last step to complete this mechanism, and it's a cleanup step. We currently have a protonated amide. So as our last cleanup step, we're going to have a proton transfer between our urea motif and our amide to generate the neutral amide and the isolable dicyclohexyl urea. It's technically more correct to show protonation at the urea nitrogen, but that's fine as drawn. That's more than okay as drawn.
Sorry, I'm a little bit lost. Oh, did I finish it or do I need to?
Yes.
Okay.
You finished the mechanism. One thing I would note is just make sure to draw out the carbonyl. But otherwise, this mechanism looks great.
Oops.
And to answer the question in the chat, you can use DCC or you can use the added base of pyridine to deprotonate. Either would work. Yeah, but this student proposed mechanism looks perfect. So let me just clear these student responses, and then we'll redraw the mechanism for our reference. So the first step, we have our carboxylic acid, and DCC will deprotonate our carboxylic acid to generate the more nucleophilic carboxylate ion. Now, after protonation, this aminium ion is much more electrophilic, and thus it can react with even weak nucleophiles, such as this carboxylate ion. So the carboxylate ion will attack our electrophilic aminium ion carbon. So from here, we now have activated our alcohol as a leaving group. So now our amine can come in and attack the electrophilic carbonyl carbon. And that in turn generates a tetrahedral intermediate. Now, if we have the choice of leaving group between ammonium and this corresponding urea group, this urea group is a wonderful leaving group. So we're going to lose this dicyclohexyl urea leaving group to generate our corresponding amide and dicyclohexyl urea. Now, as our last cleanup step, dicyclohexyl urea is going to pull off a proton, and that gives us our neutral isolable amide along with dicyclohexyl urea as a byproduct. Perfect. So the student proposed mechanism for this problem was completely reasonable. Any last minute questions on this example before we move on?
So are you able to zoom out a little bit so I can see the entire thing?
Sure, one moment. Any questions that I can address? You can show deprotonation with the urea oxygen, though it's the less basic atom. And generally you prefer to retain the carbonyl rather than draw the enol tautomer. Generally, like drawing from our discussion of the keto versus enol form, generally the keto form is preferred. And the same holds true for amides. Did that answer your question? Perfect. So let's keep going and let's talk about another method that we are quite familiar with, which is the chemistry of acid halides. So we know that acid chlorides can be prepared from carboxylic acids via reaction with thionyl chloride. You can prepare the acyl bromide or acid bromide via reaction of a carboxylic acid with phosphorus tribromide. We've already seen the mechanism for thionyl chloride, but just for your reference once again, thionyl chloride works via activation of our alcohol as a leaving group. So our carboxylic acid oxygen attacks the electrophilic thionyl chloride sulfur atom. The tetrahedral, well, in this case, not tetrahedral, but this intermediate that resembles a tetrahedral intermediate collapses. We've now activated our alcohol as a leaving group, and we've activated this carbonyl carbon because we have this strongly electron withdrawing chlorosulfite group. So even weak nucleophiles such as chloride can attack our carbonyl carbon. From here, we generate a tetrahedral intermediate, and that tetrahedral intermediate then collapses down to kick out our wonderful chlorosulfite leaving group to generate our desired acid chloride. I really like to group this discussion along with our discussion of DCC couplings because in both cases, we're activating our alcohol as a more effective leaving group. Does this method and does this mechanism to prepare acid chlorides look familiar to everyone? Okay, so let's keep going then. And let's talk about hydrolysis. This is a bit of a pointless reaction when you think about it, because in the majority of cases, you're going to prepare an acyl chloride or acid chloride from a carboxylic acid. But let's talk about this reaction just for completeness, because there are cases and there are reactions that make acid chlorides as a product, and you often treat the acid chloride with water to get an isolable carboxylic acid or carboxylate salt. So acid chlorides react with water to yield carboxylic acids. So in this case, water attacks our electrophilic carbonyl carbon. From here, our tetrahedral intermediate collapses, and that gives us our protonated carboxylic acid, which is then deprotonated by any remotely basic species floating around in solution. Not the most practically useful reaction, but it follows this general trend where you can substitute your acid chloride with functionally any nucleophile. Does this make sense to everyone? Okay, so let's keep going now, and let's talk about methods to prepare esters from acid halides. So this is an indirect method to prepare esters from carboxylic acids. So we make the acid chloride, and you can prepare generally any ester you want via reaction between the acid chloride and the alcohol under basic conditions. So esters are produced via the reaction of acid chlorides with alcohols in the presence of pyridine or sodium hydroxide. This named reaction is called alcoholysis, and generally this reaction works best with less steric hindrance. Now, one thing that I would like us to note is that generally the most reactive, aka the most electron-rich and least hindered alcohol will react first with the acyl chlorides. So if you're comparing a primary versus secondary alcohol, generally the less hindered alcohol is more reactive. So you can get chemoselectivity where if you expose this diol to, in this case, acetyl chloride, you'll be able to selectively react the primary position because it's a less hindered and thus more reactive, more accessible position. Does this make sense? Now let's talk about the mechanism for this reaction as it mirrors the hydrolysis mechanism, except this time we're under mildly basic conditions. So not enough to draw a formal anionic mechanism, but sufficiently basic where we shouldn't be drawing strongly acidic species. So in our first step, the electrophilic carbonyl carbon of our acyl chloride will be attacked with our more reactive primary alcohol. From here, we generate a tetrahedral intermediate, and chloride is a great leaving group. So we're going to kick out our leaving group, and that in turn regenerates our carbonyl functionality. From here, our base, which in this case pyridine, is going to pull off a proton, and that gives us our neutral product. So we're able to selectively acylate and react the primary alcohol over the secondary alcohol. Does this make sense? You can change the sequencing for this deprotonation step and deprotonate before the tetrahedral intermediate collapses. That's also reasonable. Any other questions on this mechanism? Okay, so let's keep going and let's talk about a variation of this. So one useful method to prepare amides from carboxylic acids and acid chlorides is via aminolysis. Amides react readily with acid chlorides, assuming you're using ammonia, a primary or a secondary amine. Tertiary amines give unstable species that generally cannot be isolated. You generate this wonderful ammonium leaving group, and this is not stable. It'll readily hydrolyze or decompose. So typically when you run these aminolysis reactions, you either use an excess of amine or you add a stoichiometric amount of base. So as we can see, we can prepare unsubstituted primary and secondary amides from acid chlorides via aminolysis. In terms of the mechanism for this reaction, it closely mirrors the alcoholysis mechanism in that our amine, which is nucleophilic, will readily attack the electrophilic carbonyl carbon. From here, we'll generate a tetrahedral intermediate. From here, we'll kick out our leaving group, which is chloride. And then finally, as our last step, we're going to deprotonate our amide, and that generates our neutral isolable amide product. Does this make sense? Wonderful. So we're at a wonderful stopping point for today. Are there any last minute questions before we archive this recording? So if we don't have any other questions, what we'll do is we'll archive today's recording.